In this video, we are going to learn the role of tensors in general theory of relativity. We are going to look into the major tensors which plays an important role in building up general relativity. We are also going to learn what is tensor, the major usage of tensor, and a fascinating history into the history of tensors, who coined the term tensor, who discovered tensor, and how Einstein with his friends and colleagues used tensors in his general relativity. This video is going to be pretty simple. We are not going to do much into the derivation portion of tensors. We are going to use illustrations, photographs, pictures so that the understanding is pretty easy with a minimal usage of mathematical equations. My name is Shaunak and you are watching this video on Physics for Students. Welcome to my channel. Before we go ahead in discovering this role of tensors in general relativity, first let us see what are the topics which are covered. I am avoiding the technical names so that it generates a basic interest and you can understand what it is. So first we are going to learn what is tensor and how it is used in Einstein's field equations. We also need to know why do we at all need to use a tensor? What is the meaning of the term covariance? And what is the history of tensor? Can we find out the origin, who coined the term tensor? And how Einstein started using tensor and relativity. Next we are going to look into why do we at all need tensors in relativity? What is the definition of a tensor? What is the rank of a tensor? How do we measure curvature on a manifold using metrictensor? How do we measure the movement of matter in space-time, that is the stressenergymomentumtensor? How matter actually deforms and takes different shape as it moves, that covers the Ricci curvature tensor, and how the vector changes when it moves along the curvature, which is an important role of Riemann curvature tensor, and finally the Einstein tensor. So all in all, this video is going to cover all the major tensors used in general relativity with simple illustrations, examples, so that the understanding is pretty clear. So first of all, what we do is that we try to find out what are the tensors that are used in Einstein's field equations. Now we all know, and previously we have seen, that this is what we call Einstein's field equation, where this R mu nu denotes Ricci curvature tensor. The R on the second part, it denotes Ricci curvature scalar. The G mu nu is basically the metric tensor. The lambda is known as a famous cosmological constant. The G denotes what is called the gravitational constant of Isaac Newton. The C is the speed of light, which is constant. T mu nu actually denotes the stressenergymomentumtensor. So we are going to learn what is a Ricci curvature tensor. Then we are looking into G mu nu, which is the metric tensor, and we are also going to understand what is a stressenergymomentumtensor. Let me tell you, other than these, there are certain other tensors which is not showing into Einstein's field equations, but we will soon discover. First of all, what is a Ricci curvature tensor? A very basic understanding and a definition. So what we can tell is that Ricci curvature tensor geometrically, it is a mathematical object that controls the growth rate of a volume of metric balls in a manifold. Now don't worry, what do we mean by growth rate of metric ball? We will soon explain. You can just understand that the Ricci tensor represents how a volume in a curved space differs from a volume in a Euclidean space. That means from a Euclidean space, if an object starts moving in a curved space, how the volume changes. In particular, the Ricci tensor measures how a volume between geodesics change due to curvature. In general relativity, the Ricci tensors represents volume change due to gravitational tides. We come to know what is called a metric tensor. It's pretty simple. It captures all the geometrics and causal structure of space-time being used to define notations such as time and distance, volume, curvature, angle, and everything. Roughly speaking, the metric tensor tells us how to compute distance between any two points in a given space. A note of caution: the word metric is generally used as a note of measurement in certain other areas, including Euclidean geometry and the normal level of geometry and physics that we do. So metric tensor is a term which is used to measure curvature and distance, but metric is a very general term which generally denotes measurements. So here is a request, note of caution to the viewers, that don't get confused with the general metric term with the specialized metric tensor which we use in general relativity. So in differential geometry it is also used to allow finding out distance, etc. The next what we come across is called a stressenergymomentumtensor. So it is sometimes also called the stressenergymomentumtensor or the energymomentumtensor. So it is basically a physical quantity that describes the density and flux of energy and momentum in space-time. It is basically a generalization of the stress tensor of Newtonian physics. We will soon see that what in details it is. The next tensor that we encounter is Riemann-curvaturetensor. Now this is extremely important. Riemann-curvaturetensor is a mathematical tool to describe the curvature of n-dimensional space, such as Riemannian manifolds in the field of differential geometry. So the Riemannian tensor plays an important role in the theories of general relativity and gravity, as well as the curvature of space-time. Well, Einstein's tensor, it is a kind of it is named after Dr. Albert Einstein. It is used to express the curvature of a pseudo-Riemannian manifold. In general relativity, it occurs in the Einstein field equations for gravitation that describes space-time curvature. Well, Einstein tensor is pretty unique tensor. It is consistent with energy conservation, which we will see, that is vanishing divergence, and it is constructed from the metric at its most second partial derivative and is necessarily an Einstein tensor. Wild tensor, the mathematics are a little bit complicated, so we are not going to explain much into what is called a wild tensor. A wild tensor is basically a kind of a tensor which named after Hermann Weyl is a measure of curvature of space-time, or more generally a pseudo-Riemannian manifold. So like the Riemannian curvature tensor, the Weyl tensor expresses the tidal force that a body feels when it starts moving into a geodesic. So the Weyl tensor differs from the Riemannian curvature tensor that it doesn't convey the information on how the volume of body changes, but rather only how the shape of the body is distorted by the tidal force. So taking all those things into consideration, what we understand now is that these are all, the tensors are all basically a mathematical tool of measurement. So we will deal with all those tensors and few more, which is the central part of general relativity. Okay, any underlying scientific theory that we encounter is based on a postulate. Now, a postulate serves as a pivotal force for every scientific theory to be successful, and general theory of relativity has a kind of a postulate which dictates the concept of tensor right at the very beginning. So it is important that we understand the postulate of general relativity, which is eventually taking us to the concept of tensor. So we can say a postulate, what is a postulate? So we can say that a postulate, sometimes it is also called an axiom, is a statement that is more or less agreed by everyone to be correct. That means this is useful for creating proofs in mathematics and in science and other social science. So along with definition, postulates are often the basic truth, or which is on a much larger theory. So postulates themselves cannot be proven, but they are, taken something to be correct. So here are few of the few things which is important. Postulates are the mathematical statements we assume to be true, or assume to be true without any proof, and do not need to prove postulates because they state it is obvious. Now, axioms play a key role in mathematics, which is true to any other sciences also. Now, you see that this picture of Sir Isaac Newton, most of the monumental work of Sir Isaac Newton is essentially based on Euclid's axioms, right? Which is augmented by a postulate of non-relation of space-time and the physics taking place at any moment. In 1905, Newton's axiom were replaced later by Albert Einstein in a special and later by general relativity. Another paper of Albert Einstein and co-workers, which is called EPR paradox, almost immediately contradicted Niels Bohr, concerned the interpretation of quantum mechanics. So this was in 1935, and according to Bohr, this new theory should be probabilistic, whereas according to the Einstein, it should be deterministic. So these are the ways in which through time we have seen that the postulates are being changed from Newton to Euclid, Newton to Albert Einstein, and then to Niels Bohr. So this is a kind of a chronology that from hypothesis we come to axiom and then to postulates. There might be some differences, but this is more or less a kind of a accepted flow in which hypothesis and postulates are coming. Why we are talking about postulate, etc., it will soon become clear. Now you see, general theory of relativity is actually based on two postulates. The first one is called the principle of general covariance. Now what it tells that the laws of physics themselves should be independent of an observer's motion. That means if I am observing at one frame of reference, it should be also true to another frame of reference. Now you might ask me a question that this was also true for special theory of relativity. Wherein lies the difference? We will soon explain. The second one is called the equivalence principle, which was done with a kind of a Gedanken term, German term, which means thought experiment, that the gravitational acceleration is the same for all observers in a gravitational field. Now these are the two postulates of general relativity, which becomes extremely important to understand in order to go from this postulate to the concept of understanding tensor. As a scientific theory is based on postulate and it dictates the basic foundation of relativity of a scientific theory, here also we see that the principle of general covariance leads to what is called tensors. So this very term covariance actually is leading us to the concept of tensors. How and where we will soon see. And the equivalence principle is something which says gravity is not a force, it's a geometric property of space-time, and gravity is indistinguishable from acceleration, which actually gives us the curvature of space-time. So this is extremely important, that if we do not understand the postulate that what is a covariance and what is an equivalence principle, we won't be able to get deep into the understanding of general relativity. Because the covariance principle itself dictates what is a tensor, and the equivalence principle dictates why gravity is a geometry of space-time and not a force. Okay, in order to go forward, first of all, we need to understand what is the term covariance and covari means. So covariance or covari is an assimilation of two terms. One is called co, that means with, and something which varies. So covariance measures the direction of the relationship between two variables. Positive covariance, that both variables tend to go high and low at the same time, and negative covariance means that one will be variable while the other will be different. Now say for example, if I get a kind of an arrow, let us forget vector, just an arrow which is moving towards this. So covariance means the next arrow will be moving maybe towards this, or this is called covariance. Or if you get an arrow which is pointing towards this, the covariance rules tells that it will go up and then right and then little bit below and then it might vanish also. So what I'm trying to tell you is that covariance actually means that to vary together with another variable, particularly in a way that may be predictive. So it is a variance obviously, but in a way which is predictive or which is stated by certain laws. This is what is called covariance. So you see the height of a person, you can call it is co-varying with the weight of that person. Now just one thing, do not forget that covariance is also a statistical tool that is used to determine the relationship between the movements of two random variables. That means when two stocks tends to move together, they are seen as having a positive covariance, and when they move inversely, it is a negative covariance. So it is used in statistics and other financial sectors. Let us not forget that. So this is what we mean by the term covariance. Now, physically, for example, covariance actually leads to this, that is a covariant tensor. So a covariant vector has its components which are, okay, so covariance is this. So if you get a variable v, a vector v, and if it moves in this way, okay, the same way, and the second variable, either it moves or transforms in the same way. So example, the gradient will halve if its components if you halve the distance, since the rate of the change of the distance is now half. Whereas contravariant is leads to something which is called a contravariant tensor. That means its change is opposite. So, and the vector has a component which changes in opposite way. So, for example, the distance of the vector is, it is this. If you take v, then it will double its components. And if you half your unit or distance, it will change in the opposite way. So, what I'm trying to tell is that the word covariance itself means that it will vary, it will change, but in a proper predictive manner, and we can understand, we can predict, or we can measure that. So variable going in this way will also move in this way, which actually leads to covariant tensor. We will come to that later. And contra actually means opposite. So the variance will lead to a tensor which is a contravariant tensor, and as you see, the vector v is in this length, but the resultant vector is double the length, so it changes in the opposite way. So this is just to give you an idea that when we call that the general postulate of general relativity is kind of a covariance, it actually means this. So you see the distance vector is doubled. So what we can tell is that we now need to create a mathematical model so that we can measure or predict the change of event in space-time. Either it should be in contravariant, that is in the opposite direction, or in the covariant direction. So tensors will help us understanding transformation properties. It will always be the same in every coordinate system, and whose components transform in a nice methodical way, which helps us for easy calculation. That is the basic idea of tensor, and as you have seen that I have earlier shown you what is the two postulates, and the reason was this, that the first postulate was telling something related to covariance or covary, and this is exactly what covariance mean, and this is the reason that we are going to find out a mathematical model which is a tensor which will vary either in contra way or in the co-way, so that the mathematical calculations becomes easy. Okay, the principles of relativity. Now this is a kind of an original paper which was later translated by Satyendranath Bose and with an introduction of P.C. Mahalanobis and University of Calcutta. Now in the principles of relativity, I'm talking of special theory of relativity. It states that the laws of physics take the same form in all inertial forms of reference. The speed of light in free space has the same value, that it is constant. Now, these are the two postulates or principles of special relativity. This one, inertial frame of reference, is something which does not experience any acceleration. This was earlier. Now what we are doing is that we are trying to find out the laws of physics should be independent of any observer's motion. That means locally inertial but globally non-inertial. That means this general relativity, which is an advancement of special relativity, will have the postulate which will experience acceleration, and it will be non-inertial difference. So the change and the varying of the acceleration in a curved space-time requires a mathematical model which will be able to help us to predict the change, and that is what is the importance of tensor, and that comes from the basic postulate of general relativity. So this is the time that we delve deep into a wonderful and fascinating history of the origin of tensors. Now the origin of the word tensor, it is coming from this Latin word which means stretches or to tender, that is some kind of a muscle which stretches. So it is a muscle that tightens or stretches, it renders, it tends. It describes also linear relations on scalar vectors, matrices and other algebraic objects. So this is the origin, which is coming from a late Latin word, which I always try to give forward, that it should be coming from the Latin word, which actually means some kind of a stretching. So now you see that when we will go into general relativity to curved space-time, which includes stretching tidal forces, this is exactly that stretching part which we will talk about. Okay, so first what we see is this gentleman in 1822, Augustin Louis Cauchy introduced the Cauchy stress tensor in continuum mechanics. So the Cauchy stress tensor is used for stress analysis of material bodies experiencing certain amount of deformations. Then in 1884, this gentleman, William Rowan Hamilton, in 1846, introduced the concept of tensors of the quaternion. Don't worry, we will look into Rowan Hamilton's original paper which cited the usage of tensor. Then we come across this great gentleman, the German mathematician, philosopher Bernhard Riemann in 1861, right, who introduced the concept of what we are learning, will be learned Riemann-curvaturetensor. And then this person, Joshua Willard Gibbs, in 1884 introduced tensors of vectors in R3, and it was called during that time indeterminate product and applied to study. He then extended it to indeterminate product to n dimensions later in 1886. In 1898, Dr. Voldemar-Voigt used tensors to describe stress and strain on crystals. In 1898, and the term tensor first appeared with its modern physical meaning here. In geometry, Gregorio Ricci used tensors in the late 1800s, and in 1901 there was a paper with Levi-Civita, whose crucial is, this is the Ricci tensor, and in 1901 Tullio Levi-Civita introduced the tensor calculus, which is very important and crucial in understanding Einstein's work on general relativity. So this is, in overall, this is a chronology of physicists, mathematicians, and how the term tensor started developing. Now, Sir William Rowan Hamilton was an Irish mathematician. He was an astronomer and physicist, and he had made a major contribution to optics, classical mechanics, and he is the first person to coin the term tensor. Now, this is the book on quaternions. Now, if you don't understand what is a quaternion, let me tell you, quaternions were first described by Irish mathematician William Rowan Hamilton in 1843 and applied to mechanics in three-dimensional space. Hamilton defined a quaternion as the quotient of two directed lines in a three-dimensional space, or equivalently as a quotient of two vectors. Now, this is the original book and this is the original paper. You see, I have underlined this. So he writes that this is something very nice. If we suppose that we call the tensor of the quaternion Q, we shall not thereby diminish the generality of the quaternion. The tensor is what was called former articles in the modulus, but there seems to be so and so. The tensor is what is called the articles. So this is the underlined in red. This is where we first in modern mathematics we find William Rowan Hamilton coining the term tensor, and this is the book in 1846 which first appeared. Now, Dr. Voldemar-Voigt also had a famous book which is written in German as this. It means The Fundamental Physics Properties of the Crystals, written by Dr. Voldemar-Voigt in 1898. This is the German version of the book, and I have underlined where he has quoted the word tensor. Just let me read it out, the important part which I have translated from German. I have therefore linked it to a special and characteristic process, just as the term vector does, and suggested the name tensors for those two-sided directed quantities. The collision with the same designation in quaternion theory, which perhaps to be feared at first, does not actually exist. That name refers adhere only to the general cause where any three mutual normal tensors occur, to the special case where these three have the same size, where accordingly the tensor triples into a scalar. The introduction of the term tensor in the sense explained above thus represents only an extension of the older meaning of the same, and doubts should not be derived from the agreement of the designations. So here is actually the English version of Dr. Voldemar Voigt in the German book where he coined the term tensor. Okay, so now we come to another great mathematician, a very close friend of Dr. Albert Einstein, Marcel Grossman. Now, Marcel Grossman was born on the 9th of April in 1878 in Budapest, Hungary. He was a son of a large machine shop owner, and he was a descendant of an old Swiss family. Now, what I wanted to tell you is that after graduation, he started at Swiss Polytechnic School in Zurich, which is referred as ETH, and in this school of mathematics, together with Albert Einstein and Mileva Merrick, the only woman in that class. In the first 2 years, he learned about calculus, analytic geometry, descriptive geometry, projective geometry, number theory, the geometry of numbers, and many others. One is very, very important is that the component of metric components of as a tensor, he first introduced you to Albert Einstein. So he introduced Riemann tensor to Einstein and the concept of general vector calculus. We will soon see in a very emotional letter how Albert Einstein expresses his gratitude to Marcel Grossman, the way he introduced and taught vector calculus, especially Riemannian geometry, to Albert Einstein. This is a very, very famous quote when Albert Einstein was trying to make things over in general relativity. He told Grossman, you have to help me or else I will go crazy. Now, yes, so Einstein encountered another genuine friend named Michel Bessot at the Swiss Federal Polytechnic School at Zurich. They shared a similar spirit as well as a very touching and a very intellectual correspondence. They spent a lot of time together. They realized something common between them, that both of them wanted to explore the truth of the universe. Now, it was Grossman who helped Einstein with the geometry and the concept of tensor algebra. He needed to formalize the theory. So he asked Grossman to search the literature and look for existing appropriate geometry to tackle questions. So here it is. So Grossman introduces tensor algebra and Riemannian geometry, and the next day Grossman returned with a solution, Riemannian geometry. He also added jokingly that the differential equations of Riemannian geometry are non-linear, which he considered as a bad feature. Okay, so this we find that when Albert Einstein started using a tensor in his general relativity, it was actually Dr. Marcel Grossman, Michel Bessot, who knew the concept of tensor calculus, and this is how they helped Einstein to formulate general relativity. Now, this is actually the top portion of Einstein's Zurich notebook. So this is this page shows that Grossman introduced relativity and theory of gravitation during the period of collaboration between him and Einstein. So this page shows that Grossman introduced Einstein to the Riemann tensor as a mathematical resource of general theory of relativity. Let us magnify this page and let us see what we can find out more. So you see that apparently Grossman had shown Einstein the relevant object that would be a path towards fully covariant gravitational field equations. Why covariant? Because we have seen that the postulate of general relativity dictates that it is a covariant in nature. Now this is the one. Now next to the definition of Christoffel symbol, this is this, and we find this one, which is Riemann-Christoffel tensor in the fully covariant form. So I am not explaining those equations, but I'm just trying to expand on the historical part, how these notes and of Marcel Grossman actually shows that. And finally we get into this one, which I've highlighted in red, actually shows the words Grossman tensor to the fourth manifold. So Grossman contracted the Riemann tensor, the amount to this operation. Now here is something important, that although we do find Ricci tensor in a 1904 paper of Gregorio Ricci Curvasto, it is not found in Ricci and Levi-Civita's 1901 paper on the absolute differential calculus. So it may therefore well be that Grossman independently invented the Ricci tensor at that point. It is just kind of a hypothesis, or you might call it. So these are the original historical papers which actually shows the help of Grossman, or the cooperation of Grossman to introduce concept of tensor to Einstein. This is a very wonderful book. If you have read, I have read it, by Abraham Pace, Subtle is the Lord, where there are certain lines which you can just read, where this problem remained insoluble to me until 1912, when I realized Gauss's theory of surfaces holds the key. And from him, it is talking about Grossman. He learned Ricci and later about Riemann, and whether my problem could be solved by Riemann's theory. So these are few lines I have taken from this book, which actually presses on the fact that how Einstein was thinking, and he was helping out with Grossman to find this. Okay. Now this book in German, it means a house for Albert Einstein, and it is a memoir document, very important for us to understand. This is the original German script, and you can see I have underlined few of those equations, especially the last one, which says the concept of geodesic. Just quickly read out the important part. The formulation still refer to the case of a pseudo-Euclidean space, but it clearly showed how the transition to gravitational field of a general kind could be achieved. Here too, the gravitational field is to be described by a kind of a metric, that is by a symmetric tensor field, G sub ik. The generalization simply consists in dropping the assumption of this field can be transformed into pseudo-Euclidean one by a mere coordinate transformation. The problem of gravitation was thus reduced to a purely mathematical one. Are there differential equations which are invariant under nonlinear coordinate transformations? This is very important. Einstein raises a doubt that are there any differential equations which are invariant, that means something which is trying to find out which is invariant, the tensor which is invariant under nonlinear coordinate transformation. Such differential equations, and only such, came into consideration as field equations of the gravitational field. The law of motion of material points was thus given by the equation of the geodata, or the geodesic line. Importantly, as you see, yes, so these are the few of the other I just spoke. So this is the original script, and I have underlined those lines which actually means tensor, and you see in German Coordinaten transformation, and so I won't dare to pronounce it, would be horrible. Next, in the same book, he encounters a wonderful event with his friend Grossman. He writes, with this task in mind, in 1912, I went to see my old college friend Marcel Grossman, who by then had been appointed professor of mathematics at the Swiss Federal Polytechnic. He immediately caught fire, although as a true mathematician, he was somehow skeptical about physics. When we were both students and exchanged our thoughts over coffee in the usual way, he had once made such a nice and characteristic remark that I cannot help it but quote here. This is the English quote. I admit that I have been benefited something essential from studying physics. In the past, when I sat down on a chair and still felt some of the warmth that came from my sitting in front, I shuddered a bit. This is completely past, for physics has taught me that heat is something quite impersonal. So the basic essence is that this companionship and friendship with Grossman actually led Einstein to formulate the tensor calculus and finally the general relativity. Okay, so we now come to the most important discussion part of our video, that why do we at all need tensors? There might be a question which is going in your mind, that can we learn relativity without tensors? So let us find it out. So we go from a flat surface to a curved surface. We get a kind of a flat surface like this x and y, and we get a vector which is called A. And what we are doing is this red line and this red line, this AY and this one called AX, these are the two components of the vector. So I hope you quite well understand what is a component. No need to repeat on that concept. So these two measures the components of the vector and the blue line. So now what we do is that we draw something on a curved space, and this xy will be the same one, but we draw it on a curved space, so the x and y takes this kind of a shape. The vector remains the same, this A remains the same, whereas the vector components, the x component which is named as A prime x and the y component which is named as A prime y goes into a different length, which you can see. So when we draw the components of the vector, what we find is that A prime x, as you can see, is longer than the original ax, and A prime y is also a little bit longer than the original ay. However, the vector remains invariant, that it doesn't change. So the basic essence is that now you see that when we are going from a flat to a curved surface, what is changing is not the vector, it is the components of those vectors. We take a kind of a further kind of a coordinate, where this ax, this one red, is the original component, and ay being the original component. These are the two lines. Now what do we do? On the right hand side, we rotated this xy. So we take a kind of a rotation. So we call it A prime x and A prime y. So now you see what happens, that this A prime x is bigger compared to the original ax, which is in a non-rotated frame of reference. And this A prime y is also shorter considering to the non-rotated ay frame of reference. From here what we find, just again to let you know, so this is actually what happens. So once we rotate, flip, stretch, whatever, the most important part is that the vector remains the same, but the components change. So from where we can call this as the vector. If the vector changes, obviously there's a problem in measurement. The vector remains invariant, the components of the vector changes, and we develop a method to measure the changes, and any mathematical entity which is invariant under rotation of coordinate system is called a tensor. So I hope things are pretty clear. So as you see that we rotate, we stretch, we flip, whatever, if the vector changes, that is a problem. So the vector doesn't changes, the components of the vector changes, and we develop a method to measure them, and this is what which remains invariant under coordinate transformation is called a tensor. So what we can tell is that in Newtonian mechanics, space and time coordinates are independent. So if this is time and this is space, let me just quickly demonstrate you with a nice example. So in Newtonian mechanics, space and time coordinates remains independent, right? So for instance, the time, so this we can also represent it as a tensor, for example. So for example, this person is throwing a ball through air and it is hitting that person, or it is reaching that person, which is independent of the speed of the observer. So what we say is that this goes in a kind of a trajectory, but when this ball goes in this way, we can measure it. When it goes in this way, and this way, in this way, and it reaches that person. In each of these cases, you will see there is a method of measurement. Okay, and most importantly, what we can say that this x, y, and z, and whatever the variables, the motion of the ball in flight is independent of the motion of the ball along the horizontal, and most importantly, they are orthogonal. Now, if we want to draw this on a curved space, so it takes a kind of a curved space like this, and we measure the same time and x, y, z, we get this kind of curvilinear space. And here's this person, and the same person is standing over there. He throws the ball, right? So these are the points where the ball trajectory will go, and here it goes up, down, and up and down until it reaches this person, right? So what we see is that these are all non-orthogonal, right? I mean to say, you need to draw those tangent lines and tangent spaces in order to measure them. So this is why this can also be framed in a tensor. So from Newtonian mechanics, where space and time and coordinates are independent, we are going into curved space-time, where the gravity of the movement is not independent. It is dependent on the curvature of space-time. That actually, makes a lot of change. So in general theory of relativity, the space and time coordinates are no longer independent. Not only are space and time affected by the velocity, they are also affected by gravity. The simple presence of mass causes the distortion in space-time, which we will see soon. So that is why you will see those manifolds and tangent bundle and tangent spaces, which we have discussed in the earlier video, comes into play. Because everything is now on curved space, we cannot measure it in using Euclidean orthogonal directions. So that is how it happens. So if you get this kind of a curved space, and these are the different kinds of, shapes. I won't say shapes. These are the different kind of masses. So you will see here what happens, that the mass which is present on the curvature causes I would say a change, a distortion in the space-time. So this one is much bigger, this one is smaller, and this one is such, right? So what I'm trying to tell is that the x, y, z, and t direction change from spot to spot from time to time. So so what we can say, that tensor equations retain their forms as we change coordinates from space and time, which is the basic idea of general relativity. General relativity also obeys the rule of diffeomorphism, which is out of the scope of this video. I have made a separate video on diffeomorphism and homeomorphism, which you can look at later on the concepts of differential geometry, which is in my playlist. Tensors, because of their transformation properties, are essential in writing GR related equations and the coordinate system independence. Let us think of space and time as a material undergoing stress and strain, and tensors describes those materials' stress and strain. Right. So this suggests that tensor is an object unto itself, not tied to any particular coordinate system, and such a notion gives us that we might expect the real world that physical measurable quantities do not depend on the coordinate system which we select. So these are the important, I would say, points of tensors, and why we use now it becomes clear that why we use tensors, because if you want to measure something and if the vector remaining the same, how will the vector components change? And this is what the method of tensor, the beauty of tensor does, that it remains invariant under the change of coordinates. Right, so now we come to tensor, and we really want to define what is a tensor. So what is a tensor? A tensor can be defined as an algebraic object that describes a multilinear relationship between sets of algebraic objects related to vector space. A tensor may also be represented as an array, a potentially multidimensional array. Just as a vector in an n-dimensional space, it is represented by one-dimensional array with n components with respect to given basis. A tensor with respect to basis is represented by multidimensional array. Mathematical objects, we can call it, that can be used to describe physical properties, and tensors can be defined a simple arrays of numbers, and in simplest form it is a quantity having magnitude, direction, and a plane to act are called tensor quantities. So this is something very, very important. We have magnitude and direction, which is represented by a vector. But what if we have got a plane to act upon? And this is the vector and tensors, you can say, the relationship, or that is the difference. So in fact, tensors are merely a generalization of scalars and vectors. Okay. So here is something which I would like to draw a note of caution to all our viewers. Now, in general, in all these stuffs across internet or in general books, etc., you will always find that tensors are generalizations of vectors and matrices. Okay, this by far caused the maximum confusion among tensors, and I can say tensors are not generalizations of vectors and matrices. So tensors are not generator vectors in any way. It's very slightly more understandable to say that tensors are generalization of matrices. No. In the same way that it is slightly more accurate if we say that vanilla ice cream is a generalization of a desert. Right. So if I say vanilla ice cream is a generalization of chocolate ice cream, then it is slightly more accurate to say vanilla ice cream is a generalization of desert, right? Vanilla and chocolate are both ice cream, but chocolate ice cream is not a type of vanilla ice cream, and desert certainly isn't a type of vanilla ice cream. So I request you that if you please do not confuse about tensors, do not compare them to vectors as you learned in physics class, and do not compare them to matrices. In fact, technically vectors are generalizations of tensors. I have to know you to trust me. And why we call it? Because we find that it is sometimes we call them as an array of numbers which leads to a matrix and which finally leads to a tensor. Right. So this is basically what causes the confusion, that we get vectors in the array of numbers, row or column, then we put it in a kind of a matrix, and then we further matrix extend the matrix into a three-dimensional form, and that is why we call them as a kind of a generalization, but actually it is not. So, okay, so before we go ahead and understand the strict definition of tensor, I would like to tell you what is the strict definition of a vector. Now, the vector set V is a vector space with the operation plus and multiplication, okay, which is any operations I mean to say, and yes, and if and only if for every x, y, and z variable is a member of V, and A and B is a member of the real number, if it is commutative, associative, identity element, inverse, associative, scalar distributive, vector distributive, and definitely this one. Right. So what we now say is that if all these are being followed, then a vector is defined to be as a member of such a space. Right. So why I'm trying to tell you is that, see, when we are trying to define a vector, it is not always those arrows. Right. We use those arrows because it becomes easier for us to imagine that we start from a certain direction, then we go up, right, left, and then use those tip to tail method in order to calculate them. But vector space are not that. I mean to say vectors. So vector is defined where all these, you can see on the screen, commutative, associative, all these properties are taken care, and vector is defined as a member of being such a space. So this is how we define a vector. It is not a vector space of arrows or just pointing each other. Now, the confusion which leads that why do people think of tensors as generalization of vectors? I will tell you what happens is that if you take a function, say for example this, then f being the linear one, it can be defined only with two values, right? Which is this, fy1, y1 fi and y2 fj. Now, if we know the values of fi and fj completely, then what we can do is that we can define f. And from there, we take a conclusion that f is a rank 1 tensor. Right? This could be, yeah. Now, the problem is that here you see that the values completely define x as well as f. Now, if this one, this dot one, especially the Cartesian metric tensor, then this values is a Cartesian metric tensor, then the values of representation of x and the values of the representation of y are exactly the same. You got it? So if it is a Cartesian metric, the values are the same. And that is the reason you take f and you call it as a rank 1 tensor, multilinear map with one increment and a one-dimensional array. So this actually causes the entire confusion. Now, so yeah, that is why people think that tensors are generalization of vectors. Whereas if we get these to be different values, then vectors by themselves are not linear maps. They can be thought of as linear maps, right? So what we can define is that a tensor is any multilinear map from a vector space to a scalar field. Also, this definition causes a little bit of confusion because a tensor is a multilinear map. So important is that matrices take a vector space to itself, whereas tensors take a vector space to a scalar field, and matrix is not strictly speaking a tensor. Right. So this is a kind of a note of caution. You can imagine tensors as generalization of matrices, etc. But that is the reason I just showed you why it is not, because if the dot product has got different values, things change. Things change very much. So this is just a kind of a strict definition. A tensor is a multilinear map from a vector space to a scalar field. Okay, so how can we summarize till now? Tensors are not generalizations of vectors and matrices. So some tensors represent two-dimensional arrays, but these two-dimensional arrays do not necessarily work like matrices. The numerical values in matrix represent entirely different things than the numerical values in tensors. Obviously, you will see that the tensor operations and the tensor definition, the values are totally different. Vectors are not always arrow, because vectors are actually something which helps us to imagine a geometric representation. And we can say that a vector is an element of a tangent space in that space-time. So mathematicians see much more than ordinary people who are trained to see vectors as arrows. Vector space is anything you like. It is a reservoir of hundreds of concepts like tangent, vector, anything. But mathematicians view in number of ways. So vector has direction in physical space. Consequently, a vector's components transform in a particular way when you change coordinate systems. If you rotate it, we have just seen it, then all vectors components change in the same rotation matrix. So this is just to let you know a few important points. Okay, can we just quickly have a round into what we call is the rank of a tensor? Now, most commonly, the rank of a tensor actually refers to the number of indices the tensor carries. So this can be thought of the dimension of multi-dimensional array, etc. So the number of dimension of a tensor has called its rank. However, different authors have different ways of writing. So if it's a scalar, it is called a rank 0. If it is this, it is called a rank 1. If it's a matrix, it is called rank 2. If it is this kind of a cube, it is called rank 3. Then we get rank 4. Difficult for rank to define rank 5 and rank 6. So intuitively, that a tensor is a physical quantity which may be characterized by magnitude and multiple directions and dimensions simultaneously. So this is just a kind of a visual representation to show you that what the rank of a tensor would be. Don't worry, we can take up a separate video on the operations of tensor. This is not the right place. So generally, rank of a tensor refers to the number of indices. Rank, order, dimension, degrees are used by different authors, and number of simultaneous is called the rank. It is called the rank of a tensor. Okay, so what we do is that now we come to what another important, I would say, tensor, which is called the metric tensor. So metric tensor, if you have watched, I have got a completely separate video on metric tensor. It means metric and tensor. So metric is basically means measurement, and tensors, as we have just noticed, are mathematical objects which follows certain rules. So there is a relation between them. So it is a coincide mathematical framework, or it transforms or obeys certain rules. So on a flat surface, if you draw a line something like this, then and on a curved surface, it transforms into a curvature. So if we can say that 1, 2, 3 up to any number n, we can take those values into a tensor, and it is called a multi-dimensional array. So this is something which we have already seen. I don't want to explain. If I've got a vector called bi, so the components of the vector changes in this, and this direction, whereas the tensor remains invariant. So if we take these 2 points and we want to measure the distance, we can use the Euclidean formula quickly to carry it. But if we get a curved surface like this, then this formula doesn't work. So what we need is a metric tensor so that it defines and computes length, infinite small distances on the manifold, and tangent vectors. We know that metric tensor is a symmetric tensor. This is the metric tensor of general relativity. This 0, 1, 0, 2 and 0, 3, these stands all to be the same, right? So what we get is the metric tensor. So G mu nu would be equal to G nu mu. So these are the 6 quick elements, unique elements, which are present in the metric tensor, and the same goes with stressenergymomentumtensor. We get 10 these are the 10 components of the metric tensor, which are, I would say, these are quite equal. Oh, I'm so sorry. This is actually those which we have deleted. Those are the duplicates, and these are the unique elements of the tensor. So it makes it to 10 components. So if we want to now calculate the distance between 2 points in a triangle like this, we ushered the old Ionian Greek Pythagoras, and we use, now we are using ds, dx and dy. Why? Because we want to calculate the differential distance. So we use the measuring the differential distance extending Pythagoras' theorem. But what if we get a kind of a curvature like this, where these are the 2 points and we want to calculate this curve? So this formula definitely won't work out. We will get some kind of a formula like this. I'm not explaining the equation, but this is a quadratic form of the equation, just like 4x squared plus 2xy plus 3y squared, right? And this dx dy denotes that they are not perpendicular to each other. That means it is not orthonormal. We have moved into the arena of curved surface, and the vectors and the measurements are not perpendicular to each other. The G denotes the amount of spread on a curved space-time. What do we mean by the amount of spread? Now, if we get a kind of a graph like this, you see the lines here are quite dense compared to these lines, which are more or less much more spread out. So this is much dense and this is loose. And this G11, G22 actually denotes the depends on where you are. That means this G is basically the metric. That means now you see that we have already calculated and we have known what is a tensor. Now we are moving this into metric. So the metric actually measures where we are and how much dense the curvature is and how much loose it is. Okay, now we take a quick example and defining what is called a contravariant metric tensor. We have noticed that contra actually behaves in the opposite direction. So we just take G mu nu and how do we define? We divide it by the cofactor and the determinant of G mu nu. So we take the covariant metric tensor in Cartesian coordinate, which is simple, and we take the first component, the cofactor divided by the determinant, and what we get is this. For this one, we get the value 1, then we calculate 1, 1, 1, 2, 1, 3, and so on. So if we quickly plot this entire value into this, what we get is this one. And as you can see, this is exactly the same G mu nu. So this is how we calculated the covariant metric tensor in a Cartesian coordinate. Now, if we want to calculate the covariant metric tensor in spherical polar coordinates, given the values as this, as you know. Now, what we get is that first we find out the determinant, which is this r4 sine square theta. Now we plot those values. We get 1, 1, 0, 0, 0, and so on. So if we now plot those values in a matrix, we get this, which is actually a conjugate. So what are those conjugated values? You see this one, and then this one, and then this one. Yeah. So these are actually what shows that it is a conjugate. So value of a covariant tensor, it is not the same, it is a conjugate, right? So this is why we say in Euclidean Cartesian coordinate the metric tensor and its components are the same. So if you really want to see, you can just go back. Let me just go back Yeah, so this one and this one is the same. I put a blue tick. But here, when we plot those values, these are not the same, they are the conjugate, right? So that is why we say that in Euclidean Cartesian coordinate, the metric tensor and this component are the same. In other coordinates, they are not the same. It's a quick example. We will use, which is very common in general relativity, which is called as a rubber sheet analogy. Okay, and this rubber sheet analogy is here. We have got a rubber sheet and we stretch a line and we try to find out the differential distance using this one, s square, and this one. We further stretch it this, and what we see is that this line and this line, the x and y, for example, it stretches, right? So we can use this one, the 2dx square element. Then we further stretch it, and this goes a long way, the 2x and 2y. So we can calculate like this. Just to show you that from rubber sheet, if you are extending those values, how do we calculate it? Now this is the stretched information. So the line actually goes in a curved manner. This is the curvilinear coordinates, right? These are the points. This is the earlier equation which we have got, right? And this is denotes that it is not perpendicular, quite obvious. So we get the unstretched information, which you just notice that by calculating the the cofactor, we got the unstretched information is the same 1001, and then we get this one G11 and G122. These are the stretching information, right? So we got the unstretched information, more or less you can say it is a Euclidean space, and the stretched information, which is a kind of a curvature. What we are going to do, I will soon explain to you. Now these two actually are the tensor which stores the information of the curvature. So if you get those lines, as you see how much and in which direction space-time is stretched. So now I hope you can relate. The stretching is what is called tensor muscles. So how much it is stretched, that is stored in a tensor. So rank 0, rank 1, these things we have already seen, and this is a rank 4 tensor, that is 3-dimensional space followed by 1 dimension of time, which is used by the genius of Albert Einstein to store the entire stretching information of a curved space in a tensor. So now when that we have got the stretched and the unstretched information, what we can do is that we can find something which is called a mapping. Now here is a sphere and this is a curved line, right? Now we magnify this sphere and then we put this stretched information, the unstretched information over here, and over here. This is called a kind of a patching, right? Then we draw those lines, these lines. They take a curved shape. So what we see is that this is the stretched and this is the unstretched information. So on the unstretched information, we have performed differential calculus and we have got the dx dy value. And this one, we can compute now distance between 2 points, any curved manifold using this equation, right? I'm so sorry, let me get back. So the unstretched information, once it is patched on a sphere, gets into a kind of a stretched information, and we can use them in order to calculate any points on a curved manifold. So how does it really help? So if we got Jupiter, Earth and Mercury, then we see that Jupiter being a heavy one, it has got a very high curvature. So we get the value of G and the weight. Earth being less heavy, it gets a less dent and we got the value of G and the weight of the Earth. Mercury being a little lesser even compared to Earth has got a less curvature, and that is why you see the value differs in terms of gravitational acceleration as well as the weight. So this actually helps us in calculating the curvatures, not only in terms of macro level Earth, Mercury and Jupiter, but on anything which is moving around the space-time manifold. That is the beauty of using tensor. Things remain invariant, yet we can calculate their magnitude. So if I know the stretching information, we can calculate distance between points. The entire stretching information is stored in the metric tensor, and what we also get is that it helps us to understand those coordinates and measure the tensor in a nice coincised mathematical framework which obeys certain rules. Recall that we defined what is called covariance earlier in this video, where we told that it varies in a nice predictable manner. So we have arrived at metric tensor that it varies in a nice manner which obeys certain rules. We come to the next important tensor, which is called the stressenergymomentumtensor. Now, stressenergymomentumtensor is actually the right-hand side of Einstein field equation, the presence of matter curved space-time. So what consists of matter? So here it is a relativistic mass coming from special relativity, the total energy of a moving body. So now here it is energy, density, momentum, flow of energy, pressure and stress. All this contains matter, and all this actually describes the stress energy tensor. So we saw energy, density, everything which consists of matter is now defined in a tensor. So in two dimension, let us quickly look. I have the red is energy density, purple momentum density, and the green one is pressure. So if I take this in 4 dimension, now you see T, X, Y, and Z. This is actually the stress energy momentum tensor. Don't worry, we will go by step by step in defining the momentum tensor. This is what it is. So the energy density, momentum, and pressure now extended to 4 dimensions. In 2 dimensions, this one is the momentum density, which is again extended in 3 dimensions. X, T, Y, T, and Z, T keeps like this. We will soon define what are those terms. And in 2 dimensions, these 2 terms, in 3 dimensions, this is the pressure. So earlier what we have got is the momentum density. Now we got the pressure density, right? So this is the pressure density, and these are at the bottom some of the extra terms which is there in the tensor. So here is the stress energy momentum tensor. It is an extension of the classical Newtonian stress tensor. It is also a relativistic extension. It describes emerging momentum flux through space-time. Now, if you look at, because it is an extension of the Newtonian tensor, earlier when we talk of pre-relativistic era, then this space-time 4 vector is defined as this, right? And this takes place into this. We will explain those terms. So this is the energy, the momentum in X direction, momentum in Y direction, and momentum in Z direction. So this is what is the momentum in all the 3 directions. But just note, this is actually a vector because we are dealing with a pre-relativistic era. But what we need is a tensor. So now let us reform them into this. Here you will see this is part comprises the momentum density. This one. This also comprises the momentum density. This is the energy density. This one is the shear stress. This one is the pressure. And this one is the momentum flux. Now you will see that E equals to mc squared. This part, every part of energy that we are thinking will find a house in this tensor. Now E equal to mc squared, that T00 will always find the top position. Why? Because of the speed of light. Because of the speed of light is so sheer and so high that it is always at the top. So this explains that whatever matter content of this universe that we are talking about, energy, rest, mass, stress, will always find a place in this stress tensor. And that is why the energy tensor tells us how matter is formed and it causes a curvature in space-time. So this is energy density. You can call it as the amount of energy stored in per given space. Energy flux is the rate of transfer. We got momentum density, we got momentum flux, the pressure and the shear stress. Momentum density is the momentum per unit volume. Momentum flux is the rate of change of momentum flowing through unit area. This is the pressure and the shear stress. So these are the meaning of the terms. So we dealt with energy density. It is the energy that is responsible for the space-time curvature. Pressure, here a person is squeezing some matter in hand, that also acts as a source of space-time curvature. And when the matter moves across from one place to another, this flow of energy flux also causes the curvature. So energy density responsible for the curvature. Pressure is also a source of space-time curvature, and the energy flux which also causes a curvature. Then we find what is called a momentum density, that is mass flow multiplied by momentum or mass. And this photograph actually shows, so we got energy and momentum and pressure and stress, and this actually forms the curvature. So this is another important tensor of what you call general relativity, which is responsible for the matter movement. So here we summarize energy, momentum and pressure. It is d mu nu, and this is got at zero divergence. Don't worry, this is the Riemann-curvature-tensor, which we will explain later. It is energy, not mass, that is the source of gravity. And just remember, this zero divergence of stress energy tensor, is it the same as conservation? Yes, but the ordinary divergence does not vanish. The covariant divergence vanishes. So here it is, the final quadrant. We have covered energy density, the energy flux which moves through space from one point to another, the momentum density, and the stress tensor. We come next to what is called the Ricci curvature tensor, and I will try to explain it quite easily. Ricci curvature actually measures how a shape is deformed as it moves along the geodesics. So let us take these two, x and y, and these are the crazy curvilinear coordinates. Here is a point, and you see when it moves along, it goes up, and when it curves down due to the curvature. Another point, when it tries to go around here, it goes up and it curves, and it seems that they are meeting at some point. So the two initial parallel geodesic, which started at some point of time, deviated or converged due to curved space-time. And in the presence of the curvature, these geodesics starts to deviate and the space-time volume starts changing. So I won't go much detail into the mathematical part. What we will do is that we will just explain this Riemann curvature tensor leads to Ricci curvature tensor, which leads to Ricci curvature scalar. And you will see that Ricci scalar is a contraction of Ricci tensor. I have dealt Ricci tensor much in details in my earlier videos, so I just wanted to explain what actually it does. So Ricci tensor scalar is a contraction of Ricci tensor, which is again a contraction of the Riemann curvature tensor. We'll see what is Riemann curvature tensor. So Ricci curvature tensor then tracks volume change along the geodesics, which means how volume move and shrink. Depending on the curvature, Ricci curvature shows that whether it is static, it is going or increasing. So when a volume is moving through a curved space-time, how it is going or decreasing, that is being denoted. Now when we talk of volume change, we mean to say the change of volume on the linear and orthogonal and non-orthogonal plane. Now when we talk, say for example, back to school days, we determine using determinant to calculate the area of parallelogram. So we use this, quite simple. Area of a parallelogram is this, right? Now what do we mean by volume growth? Now say for example, in a one-dimensional linear transformation, it is straight, right? So this is a line. So you see 0, 1. Once it is moved to a different extended one, 0, 3, we will see that T maps the interval 0, 1, 0, 3, and the determinant of the matrix associated with T is 3, which means that T stretches the object and increases by a factor of 3. So this is a 2D linear transformation, and it actually shows that it has increased to 3. Now a stretching of two-dimensional linear transformation, you see this cube, once it has stretched into this quadrant, right? So you see that it rotates by pi radians and stretches to increase by an area by a factor of 4. That means it has stretched to two-dimensional in a linear transformation. Now if I want to stretch some material, you see that entire thing has been stretched. So the blue, which is on the left hand side, appears on the right hand side. The yellow, which is on this portion, appears again on the right. The red has shifted to the corner, and the green has shifted entirely to the left. So it doubles the area, and the orientation is also reversed. This is doubling, and the orientation is reversed. And what happens in a 3D linear transformation? If you take a matrix like this, A1, A2, So the 3D linear transformation goes something like this. So what happens is that the determinant increases by 12. That means that it rotated the cube and stretched it to a parallelepiped with a volume of 12. So the expansion of volume by t is reflected by the fact that the determinant of A is 12. So this is what we mean by transformation or volume transformation in different coordinate system by stretching, flipping, and so on. So what we got? A transformation's determinant specifies how the volume changes. If it is negative, there is a mirroring, which results in preserved. When orthogonal transformations are applied, then the shape is preserved. So this is a cube, this red one. Now we stretch it to a cuboid. You'll see what happens, that the line increases to this. So this is a sphere, and this is an oblate spheroid. So this line, when it is stretched to an oblate spheroid, you see it goes like this. So these is actually what we mean by a linear transformation on volume changes under linear and non-linear transformation. Now, all these were on orthonormal basis, that means it deals with perpendicular path. Remember, general theory deals with non-orthonormal basis rather than an arbitrary system. So here we have to introduce, in order to calculate in a non-orthonormal system, what is called a volume elemental form. And I'm not going into the details of this. Just let us understand that volume form is a special differential form defined on a Riemannian manifold, which introduces a natural concept of measure on a manifold, and it is a tensor. And these actually leads to geodesic movement on curvature. The volume changes, it shrinks and grows. I am not going that again because the video is already quite long. You can look into the earlier video of my beginner's guide to the general relativity where I explain the geodesics. Finally, we come to the most important and very intrinsic part of what is called is a Riemannian curvature tensor. This actually the Riemannian curvature tensor involves a lot of mathematics, but we are not going to deal with this. This is how a Riemannian curvature tensor looks. Don't worry about this. So in the mathematical field of differential geometry, the Riemannian curvature tensor, which is also called Riemann-Christopherson tensor, is the common way to express the curvature of a Riemannian manifold. So the Riemannian curvature tensor is a tool used to describe the curvature of an n-dimensional space such as Riemannian manifolds in the field of differential geometry. This actually will involve three things: parallel transport, covariant derivative, and Christoffel symbol, which would require a little bit more mathematics. We are not covering this in the video. I will just cover up the basics so that you will be able to understand. So Riemannian curvature tensor gives a complete description of any curved space, and Ricci tensor is a contraction of Riemannian tensor. So here you see the Einstein field equation, and where is the Riemann curvature tensor? Right, so it is nowhere. We define Ricci tensor, we define metrictensor. Where is the Riemann curvature tensor? Here it is. Now this one, this R, is actually the Ricci curvature tensor, which is basically a contraction of the Riemann curvature tensor. That means it is hidden. The Riemann curvature tensor is already there, but it is a kind of a contraction, so we are not going to see it. Okay, so the Riemann curvature tensor, as you see, this one is the Ricci tensor, this is the Riemann curvature tensor, and Ricci curvature tensor is a contraction of the first and the third. So this is the first index, and this is the third index, and this has been contracted. Now, each component of the Ricci tensor is the sum of multiple components of Riemann tensor, which something looks like this. Okay, so what is the geometry? How can we visualize? Okay, before I go into this, I need to explain to you what is called a parallel transport. Now, in geometry, parallel transport is a way of transporting geodesics along the smooth curves of a manifold. Now, a parallel transport, you can say, provides a way to compare a vector in one tangent plane to a vector in another by moving the vector along the curve without changing it. Okay, so for example, I am standing at this point. I want to go at this point. So I now need to move, keeping my head or the arrow that I'm carrying as straight as possible. This is the blue arrow. So I try to make it as straight. This is the B, this is original. So try to make it straight, but still I'm trying to make it straight, but you see still it is curving. So this is the curvature. Now from here, if I want to move up to here, if I try to make things still straight, it will point to this, 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 and this. Right? So the direction of the vector changes due to the curvature. Now from here, if I go back to my original, this red point, I'm trying to keep my arrow straight, but it still curves and curves until I reach to this point. Okay, now if I take out this new vector d prime and the original vector d, I take out those and I try to measure what is actually the difference. This is actually the original and the changed vector. This is what Riemann actually curvature tensor does. So the Riemann curvature tensor describes the change of all the components of this vector in space-time direction. Okay. That means if you see in a Euclidean plane, it will be the same. If I start with one point, we'll come back to the same point. The vector arrow doesn't change. But only when the vector takes a different shape after coming back from the original point, traversing across the sphere or a curved manifold, that means it has undergone a change. And what amount of change it is this? This is basically what Riemann curvature tensor describes. So this is the curvature tensor again defined, and this is what this shows. So it also denotes that it gives a complete description of the tidal forces of general relativity, which is also related to stretching as you know. So this is what is, I would say, it is not typical to Riemann curvature tensor. It's a kind of an analogy after parallel transporting it, how the original vector, the transported vector changes up to what degree that is measured. But here is a problem. The problem is that in case of a parallel transport, we try to keep the vector constant, but it is not always possible. Right? So parallel transport cannot keep vectors constant. So what is the way out? Here we introduce something which is called a covariant derivative, which we will explain it later in video. It looks something like this, where u denotes the direction, v is the vector field, and it denotes the rate of change of a vector field. And covariant derivative is a tool which helps us to find parallel transported vectors. Right? So it helps us to find out the parallel. So this is actually a kind of a understanding of Riemann curvature tensor, and parallel transport doesn't help us to keep the vectors constant, which is dealt by covariant derivative. Okay, so finally what we come is the Einstein tensor. Einstein tensor, to be very honest, doesn't have much to deal with it. So it is actually known as the trace reversed Ricci tensor. So if you take this Einstein field equation, then this one G mu nu becomes the Einstein tensor. So it is defined in terms of Ricci and Ricci scalar. So this is the original equation. We take this one out and denote it as kappa, the Greek letter kappa. Why? Because these are all a bunch of constants, right? These are a collection of constants. So we substitute this, and what we get d by g is actually counterpart of Newton's gravitational constant. So what we get is that this g mu nu is a symmetric tensor. It has also got a zero divergence. As you see, g mu nu provides curvature of spacetime because we have just contracted the Ricci part, and t mu nu because it denotes what is called a matter energy presence. So if this has got a zero divergence, this has to have a zero divergence so that the books balance. And remember one thing here, that the ordinary divergence of the stressenergymomentumtensor doesn't vanish. It is the covariant divergence. Because you might ask a question that is it similar to the conservation of energy? Yes, but not the ordinary one, which is the covariant divergence one. So here are a few points which I would just like to take a note on this, that most obvious reason is that the vanishing of the divergence is set to zero due to its connection with the stress tensor, and is defined as this. When these gamma are connections, these are Christoffel symbols. We will discuss it later using the metric. Now, the problem is that general objects like tensors forms do not have single value, but they have a set of numbers, and these numbers are related to a specific choice of the basis of the vectors at each point. So the curvature of the space-time is defined by Riemann tensor. This connection actually tells you how to differentiate the objects that are not scalars, right? So, and the problem is that you cannot tell this until the basis is constant. So we can now differentiate the components of the tensor, and until we differentiate the components, we cannot tell that. So if we get zero, our space is flat. We saw that, and it is any other value, it is curvature. From a physical perspective, the curvature of the space-time is induced by the presence of matter. We have seen that, and that is a four-dimensional version of the stress tensor. This generalizes stress formula to Minkowski space that the addition of pressure leads to improve the energy of its flux. So when we proceed from flat space to a curved one, you have to replace those ordinary derivatives with covariant derivatives. Hence, if the geometry is produced by energy momentum tensor, whatever is on the other side of the equation, it must be a vanishing divergence, and that is how Einstein originally guessed the equation. So that is how the connection, which will come later when we talk about the Riemann curvature tensor, how it is related to Christoffel symbols, etc. So this is a kind of a nice summary on those parts what we have learned. So that's it, a very long video with a lot of details coming to an end. Let us quickly summarize them, what it is. We have understood the use of tensors in Einstein field equations. What are the postulates of general relativity and how it leads to the term covariance in two domains. A wonderful history of tensor, sorry for the spelling mistake. How Einstein got to the idea of tensor. The need for tensor in general relativity. Why do we need? Yes, definitely we need that. Otherwise, we won't be able to calculate. Tensor, what is the definition? What is the rank of a tensor? The most important metric, the stressenergymomentumtensor, the Ricci and the Riemann-curvaturetensor, and lastly, the Einstein tensor. I would like to thank all of you for the last video, which you have really commented, liked, and shared so much. Thank you for that. In the next video, what I would like to do is to expand more on the Riemann curvature tensor part, making it as straight, as simple, and as clear as possible. Do let me know your comments in this particular video. Please like, share, and subscribe. And I'd like to hear your comments on how you like this video. Stay safe and stay happy. And this is Shaunak signing off from Physics for Students, and wish you a very happy weekend ahead, and promising you to come and see you very soon with a new set of videos. Bye and take care.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.